Good. So let's now take a numerical example. This is problem 6152 in Cidra's book. Okay. So what's required here? So you have here the problem in the book. It gave you beta as a range from 50 to 200, and it asked you to solve the circuit once at 50 and once at 200. So we're gonna solve it at 100. So we can assume that the beta is 100, and we're gonna solve it, at this only at this value. It should be at 50 and 200 should be the same. Same analysis, of course, not the same numbers. Okay. So what's required here is basically find AV, our input, our output, and AV. Okay. First, is this a common base or common emitter or common collector? Basically, the input is near the base. Here is the base and here is the input connected to the base, and the output is connected to the emitter. So it's a common collector amplifier for emitter follower. Okay, let's remove that thing here. Okay, so let's solve it. Solution. Okay, so first DC analysis. In DC analysis, the capacitors are open. So we just remove this part and also remove this part. So the circuit will be reduced to the following one. RE, VCC equal to 5, and RB here, which is 100 kilo ohm. Let's call it RB. Yeah, and that's it. So IE from that loop here, IE is equal to. So let's do it in, not to confuse you. So what's flowing here is IB, and what's flowing here is IE. So IERE plus 0.7 plus IB RB equal to VCC. IE RE plus 0.7, and IB is IE over beta plus 1. And you can, ignore the 1. That's fine also. RB equal to VCC. So IE equal to 5 minus 0.7 over RE plus RB over beta plus 1. Beta is 100, RE is, it's given 1 kilo ohm, and RB is 100 kilo ohm. So this will give you how much exactly? This will give us, I didn't write it down. No, yeah, 2.16 milliamperes. Once you get IE, you get RE. RE small is equal to VT over IE. Or you get RBI as well. So RBI is equal to RE multiplied by beta plus 1. So RE is VT over IE multiplied by beta plus 1. If you substitute, this will be 1168 kilo ohms. You can use RE small or RBI, that's very fine. Okay. Now we finished the DC analysis, so let's go now to the EC analysis. Oh, I'm not sure how to do that. Yes. So AC analysis. Number 2, AC analysis. In the AC analysis, short circuit on the capacitors, remove the DC sources. Okay, so if we did this will be shorted. This will be shorted. Capacitor, this will be shorted as well. So first start by the AC model of the transistor. So beta IB, here is R by, here is IB, collector, base emitter. So the collector is directly connected to the ground. The emitter is connected to the ground through two resistances, RL and RE, because now this is shorted, so this will be in parallel with this. R load, RE. And finally, the base is connected to the ground through, we have two branches here. Between the base and the ground, you have this RB. And the other branch is R signal and V signal. And before we continue, here is V input and R input, and in the future R output. Okay, so let's start first by R input. Our input is it will be the resistance seen between these two terminals, this and the ground. So it will be RB parallel the resistance seen here. So let's call this R input dash. Okay. So if we assume this current is called I input, let's assume so. And here is the voltage V input. So R input dash equal to V input over I input. I input first is equal to IB. Basically, IB is flowing in that branch, so it's just IB. How about V input? So you just make a loop here and you will get it. So V input is equal to IB R by plus the current through here is IE, which is beta plus 1 IB flowing in both resistance in parallel. So the voltage here on RE or RL is the same because they are parallel, equal to beta plus 1 IB RE parallel RL. Let's now substitute this. So R input equal to RE capital parallel R input dash, which is V input over I input. V input is IB as a common factor. This will give us R by plus beta plus 1 RE parallel RL over IB. IB will go with IB. So R input equal to RB capital parallel R pi plus beta plus 1 RE parallel RL. Very nice. So let's have now a common sense for the numbers. So basically, RB is 100 kilo ohm parallel with R by is 1168 kilo ohms plus beta is 100, so this is 101. RE is 1 kilo ohm. Parallel RL is also 1 kilo ohm. This is equal to 100 kilo ohm. Parallel 1168 kilo ohm plus 101 multiplied by half. So this is 100 kilo ohm parallel 1168 plus 50.5. So it's 100 kilo ohm approximately parallel to 50, something like 51 kilo ohms. So if we did the math, our input is 33.84 kilo ohms. Okay, which is big. I will say, after we finish, I will show you two situations. One with this circuit, and one if we just connect the load we have in the circuit directly to the input. We're gonna see both applications and how common collector actually solves, or enhances the performance of the circuit. Number two, RO. RO is the resistance seen by RL. So we're gonna remove RL and put a test voltage source, VXIX, some imaginary voltage source, and RO will be VX over IX. Good. So we're gonna draw the same circuit again. So I'm just copying it and paste. Good. So we're gonna remove RL. And put testing source VX reducing IX. And of course, we're going to cancel the source. So we have here one independent source, which is V signal. So we're going to short it. So RO will be Vx over Ix. Okay. I'm going to simplify it a little bit. So beta IB Vx Ix and here RP capital and R signal are actually in parallel. So I will just draw one resistance, which is RB capital parallel R signal. Here is R bar. Here is RB. And the current here is IB. So from that loop here, from loop one, what we have? We have Vx, and we have this voltage IB R by, and we have this voltage IB RB capital parallel R signal equal to 0. We have one loop, three elements in that loop, the voltage source, R by, and RB parallel R signal. So Vx basically equal to minus IB as a common factor, R by plus RB parallel R signal. How about this node? At that node, you have Ix going into the node. You have beta IB also going into the node. You have IB also going into the node. And you have this current here, the current of RE going out of the node. So this is equal to the current of RE. Current of RE is just the voltage across RE over RE. The voltage across RE is Vx. So Vx over RE. So let's remove Vx now and put its equivalent, which is minus IB multiplied by this factor here. So Ix plus IB beta plus 1 equal to minus IB R by plus RB parallel R signal over RE. So from this, Ix equal to minus IB. Let's take minus IB as a common factor. So this will lead us to beta plus 1 plus R by plus RB parallel R signal over RE. Okay. Good. Now let's find RO, because now V input or Vx and Ix both are function of IB. So we can divide them safely and IB will just go away. So RO is equal to Vx, which is minus IB R by plus RB capital parallel R signal over Ix, which is minus IB again. Then we have beta plus 1 plus R by plus RB parallel R signal over RE. Minus IB will go with minus IB. So this will give us R by plus RB parallel R signal over beta plus 1 plus R by plus RB parallel R signal over RE. Okay. Before we continue, remember in the first example that I gave for the common collector, RO was R by plus RB plus R signal. It was like this. It was R by plus R signal and both over beta plus 1. Okay, so we need to check now. We need to check if we are in the correct path or not. So to check on yourself, both R by equal to infinity, because in that example that we solved it in the beginning, there was no RB, which means RB is equal to infinity, and there was no RE, which means again it was infinity. So let's do it by one by one. So let's sorry. So one by one here. So let's do it with another color. If RE equal to infinity first. So what's going to happen? This is easy. If this is infinity, so this term here will just go away. So RO will be equal to R by plus RB parallel R signal over beta plus 1. Now second step, both are P capital equal to infinity. You know that if you have a parallel combination and one of the signals are infinity, the parallel combination will go to the second resistance. So RO, R by plus our signal over beta plus 1. We go back to the original value. So we are in the correct way. Okay? The only difference between the circuit and the circuit that we solved in the previous, the first example of common collector, there is RB, it's not infinity. There is RE, it's not infinity. So if we put infinity for RB capital and RE, we should get the same value that we got before. Good. Now let's have a sense of numbers. So let's substitute and see. So RO equal to all that stuff here. So let's substitute for the number and see what we're gonna get. So our R by is 1168 plus RB parallel R signal is 909 kilo ohms. Beta plus 1 is 101 plus R by again 1168 kilo ohms plus RB parallel R signal against 909 over 1 kilo, which is, it's just one, right, one, which is R. Okay, so it's basically, around 10 in the numerator, divided by 101 plus 10 again. So it's like 10 over 101. Oh, sorry, 111 or 110. So it's approximately, 10 or something. So if you did the math here, the output will be 92.2 ohms, not kilo ohm, 92.2 ohms. Okay, which is very small. So the R input was around 33 kilo ohm or 34 kilo ohms, and here RO is in ohms, 92 ohms, very small. Okay. Finally, AV, number 3, AV. AV is equal to VO over V input. We need again the circuit, so let's paste it again here. Okay. So the input is the voltage from that point to the ground. Okay. And VO is here. Is the voltage across RL or RE. So VO is equal to the voltage, sorry, the current through these two parallel resistors, which is beta IB, beta plus 1 IB, multiplied by RL parallel RL parallel RE. So this is VO. The input from that loop, which is still drawn here, this loop, let's call it loop 1. The input is equal to IB R by plus VO. And the VO is beta plus 1 IB RL parallel RE. So AV equal to VO is this thing here, beta plus 1 IB RL parallel RE over R by, and IB is common factor, plus beta plus 1 RL parallel RE. IB will go with IB. And if we substitute here, this will be 0.977. Approximately 1, right? It's very close to 1. 9.997. You can say 98. It's very close to 1. We finished. But let's now analyze the advantage that we get from adding this common collector. So the original case should be something like this. So let's have a line here. Let's examine the two situations with no common collector stage between the source and the load, and here with common collector between them. If we don't have a common collector, we have the source, V signal, and the R signal, which is 10 kilo ohms, directly connected to the load, which is 1 kilo ohm. So VO here is equal to V signal multiplied by 1 over 1 plus 10, which is it's V signal over 11, which is around it's around 0.1 V signal. 10% only reaches, so 10% of V signal reaches the load. Now what happened after adding the common collector? So here is V signal again, 10 kilo ohms again, then our input, which is 33.84 kilo ohms. Then we have here AV, V input, and V input is here across our input, and the AV is 0.977. Then we have our O, which is 92.2 ohms. Then we have the output, which is 1 kilo ohm. Good. So first, V input is V signal. Our input is 33.84 over 33.84 plus 10 kilo. This is basically 0.77 V signal. Good. So AV, so here is V output. V output is equal to AV, V input. We have AV is 0.977, and V input is 0.77 V signal, so that's known. Okay, multiplied by our load over our load plus 92.2. So that's AV is 0.977. V input is 0.77 V signal, and our load is 1000 or 1 kilo ohm over 1 kilo ohm or 1000 plus 92.2 ohms. So if we do the math here, VO will be equal to 0.688 V signal. So here around 70% of V signal reaches the load, while here it was only 10%. So that's actually the advantage of having this common collector amplifier. Okay, guys, so that's all for the common collector. Okay, and next lecture we're gonna talk about multi-stage amplifiers, multi-stage BGT amplifiers, and then we finish the BGT amplifiers, and we go to another transistor, which is the NMOS transistor. Okay, and thank you very much, and have a great day. Bye-bye.